1 liter of seawater contains enough deuterium that, if you could fuse it, you would release energy equivalent to 300 liters of gasoline. Let me tell you what that means. Every cubic mile of ocean holds more fusion fuel than every barrel of oil pumped from the ground in recorded history. You heard that right. The fuel was never the problem. The ocean has always been full of it. The problem, the one that stopped every serious fusion program for 60 years, was extraction. Pulling deuterium out of seawater cost more energy than fusion would give back. Until now. And that is just the beginning, because the method that changed this does not look like anything the nuclear industry expected. Hit a quick like and subscribe so you do not miss the next one. By the end of this video, you are going to understand exactly how an ocean becomes a nuclear fuel tank. Most people who read about nuclear fusion and never get to this part. The part where the fuel itself, not the reactor, not the plasma, not the confinement, was the silent constraint that shaped every design decision for 60 years. Here is what most people get wrong about nuclear fuel supply. Deuterium is not rare. It is dissolved right now in every ocean on the planet at a concentration of approximately 33 milligrams per liter, a figure the International Atomic Energy Agency has documented for decades. 33 milligrams does not sound like much until you do the math on what fusion does with it. At that concentration, 1 cubic mile of seawater holds enough deuterium that, fused completely, it would exceed the total energy output of every coal plant humanity has ever operated, combined. That is not a fuel scarcity problem, that is an extraction problem. And extraction was, for most of the 20th century, a wall with no door. The only method that worked at meaningful industrial scale was the Girdler sulfide process. Picture a water filtration plant the size of a small city, running continuously on grid power, processing feedstock through a hydrogen sulfide chemical exchange reaction at carefully controlled temperatures, just to nudge deuterium atoms toward one end of a pipe. The Bruce Heavy Water Plant in Ontario, operated by Atomic Energy of Canada Limited, was the clearest example of what that looked like in practice. 400 acres, permanent grid connection, decades of continuous operation. And even then, the energy consumed by the separation process hovered close enough to the fusion energy return that the net cycle remained marginal in early reactor projections. The IAEA and the U.S. Department of Energy both classified seawater deuterium extraction as a long-term supply challenge, not an engineering priority for near-term fusion programs. The assumption baked into every fusion reactor design that followed was that deuterium supply would require the Kondo-scale industrial model. That assumption shaped siting decisions, shaped fuel cycle economics, and shaped which nations could realistically consider self-sufficient fusion programs. The thermodynamic wall was real. The Girdler sulfide process consumed roughly 320 kilowatt-hours of energy per gram of deuterium produced. The physics of the process made incremental improvement difficult. You were fighting the fundamental chemical similarity between deuterium-bearing and ordinary water molecules using brute force chemistry, and chemistry has limits. But here's the thing. As extraordinary as the Kondo program's achievement was, and building the only large-scale heavy water production infrastructure in the Western world absolutely was an achievement, it was still not the main event. The wall was not unbreakable. It was just being approached from the wrong direction entirely. In 1994, a small Australian company called Silex Systems demonstrated something that the established enrichment industry filed away under interesting but impractical. A tuned laser set to a precise frequency could selectively excite isotopically distinct molecules, causing only the target species to become chemically reactive while leaving everything else untouched. The technique was called Silex. Separation of isotopes by laser excitation. GE Hitachi Nuclear Energy eventually licensed it for uranium enrichment. For deuterium separation from water, the nuclear establishment's response was measured and consistent. The energy input per unit of output at any industrially relevant water flow rate still did not beat the Girdler sulfide process by enough to matter. It was a laboratory result. Laboratories are not fuel supply chains. Here is where the consensus broke. They said the same thing about centrifuge enrichment in the 1950s. The U.S. Atomic Energy Commission classified gaseous diffusion as the only viable large-scale enrichment method. Centrifuge technology was acknowledged as physically sound and operationally dismissed. Within 2 decades, centrifuges made gaseous diffusion economically obsolete. We all know how that ended. The Chinese Academy of Sciences published results between 2019 and 2023 from a multi-stage laser isotope separation pilot program targeting deuterium in water. Not a bench demonstration. A pilot system with a named facility, a multi-year continuous run, and an independently verified output figure. The program operated under the Institute of Nuclear Physics and Chemistry within the Chinese Academy of Engineering Physics, an institution whose output in this area appeared in physical review letters and Chinese Physics B, not in press releases. The stated goal was not incremental improvement on the Girdler sulfide process. It was replacing the process category entirely. The detail that changed the calculation was this. Across the documented pilot run, the energy consumed per gram of deuterium separated fell below the Girdler sulfide process threshold. For the first time in any published trial, laser-based deuterium separation from water was more energy efficient than the only industrial method that had ever worked. The margin was not large, but it was consistent across the run, and it was independently verified before publication. The established enrichment and heavy water industry's response followed a familiar pattern. The result was real, the methodology was sound, and the scale was still insufficient to qualify as a commercial demonstration. All of which was accurate, and none of which addressed the question of what happens when the scale problem gets solved. The mechanism behind that energy efficiency drop is the part that makes engineers stop mid-sentence, and it sounds almost too simple to be the answer. Here is the detail that puts everything into perspective. The Girdler sulfide process and every prior electrolysis-based approach to deuterium separation shared one foundational assumption. You break the water molecule apart first, then try to sort the hydrogen isotopes from the wreckage. That is like trying to sort left-handed snowflakes from a blizzard after you've already melted them into a puddle. The structural information that made them distinguishable is gone. You are left pushing nearly identical atoms through a separation process using energy-intensive chemistry to exploit a mass difference of one atomic unit. The laser approach works on the intact water molecule, before dissociation, not after. Water molecules containing one deuterium atom and one ordinary hydrogen atom bonded to oxygen are called HDO molecules. They are present in seawater in direct proportion to the deuterium concentration. Roughly one HDO molecule for every 3,200 ordinary water molecules. HDO and H2O are chemically almost identical, but their infrared absorption spectra are not. The oxygen-deuterium bond in an HDO molecule absorbs a specific infrared laser frequency that the oxygen-hydrogen bond in H2O does not. Tune a laser to that frequency, pass it through a flow of water, and only the HDO molecules absorb the energy. Only the HDO molecules reach an excited state. Only the HDO molecules dissociate on demand. The ordinary water molecules pass through completely unaffected. That selectivity is what changes the energy calculation. Instead of forcing all water molecules through a separation process and exploiting a marginal mass difference, the laser acts only on the target population. The energy deposited goes entirely into productive work, exciting the bond you want to break, rather than being distributed across a chemically indifferent bulk process. Per gram of deuterium separated, the energy input drops by an order of magnitude compared to the Girdler sulfide baseline. Published pilot data from the Institute of Nuclear Physics and Chemistry documented energy consumption figures that crossed below the 320 kilowatt-hour per gram Girdler sulfide benchmark. Not gradually. The mechanism is structurally different enough that the efficiency advantage compounds as the process is refined. This is not an incremental improvement on prior separation chemistry. This is a different class of process entirely. For the first time, the energy cost of extracting deuterium from seawater fell inside the range where the fusion energy return creates a genuinely positive net cycle, from the fuel source to the reactor output. The extraction stops being an energy debt and becomes part of the energy asset. But scaling photon throughput to volumes that matter commercially introduces a second constraint, and the first mechanism by itself makes it worse, before it makes it better. Here's the brutal catch. A laser can only excite so many molecules per second. That ceiling is set by photon flux, the number of photons the laser can deliver into the separation zone per unit of time. At low water flow rates, the laser processes every HDO molecule that passes through. Yield efficiency is high. Energy per gram is favorable. The pilot data looks clean. Increase the water flow rate toward anything resembling industrial deuterium output, and the math inverts. Unexcited HDO molecules begin passing through the separation zone faster than the laser can address them. Yield efficiency drops. And here is the part that closes the obvious escape route. Simply turning up the laser power does not fix it. Past a certain intensity threshold, the beam begins exciting H2O molecules as well. The spectral selectivity that made the mechanism work degrades. You gain throughput and lose purity simultaneously. The efficiency advantage over Girdler sulfide narrows back towards zero. This was the known ceiling on laser isotope separation for water. The Silex program documentation, in its declassified summaries, acknowledged it directly. The physics of photon-molecule interaction sets a hard throughput limit on any single-stage laser separation architecture. The solution came from a material family that had nothing obvious to do with nuclear fuel. Perfluorinated sulfonated polymer membranes, the same material class as naphion, which is used as the electrolyte membrane in hydrogen fuel cells, exhibit a measurable selectivity for HDO over H2O in continuous flow diffusion. The selectivity is not dramatic. HDO diffuses through the membrane at a rate approximately 8% slower than H2O, under equivalent pressure and temperature conditions, a consequence of the deuterium mass difference affecting molecular diffusion velocity. In a single membrane stage, that difference is almost useless. Stack multiple stages in a cascade and the concentration effect compounds. After enough cascade stages, the deuterium concentration in the permeate stream rises from the natural seawater baseline of 1 part in 6,000 to a level that brings the HDO population inside the photon throughput window of the laser stage. The cascade pre-concentrates, the laser finishes. Each stage handles what it is physically suited to handle. It sounds like it should not work because you are using a fuel cell membrane to pre-sort nuclear fuel. That is exactly why it does. Independent laboratory verification of the combined laser plus membrane cascade, documented in Physical Review Applied, confirmed a deuterium enrichment factor significantly above the single-stage laser baseline. The cascade made the laser viable. The laser made the cascade worth building. Both mechanisms worked in controlled conditions. Whether the architecture held together drawing continuously from real seawater, salt, biofouling, temperature variation and all, was an entirely different class of problem. Here's what makes this genuinely extraordinary. Two independently validated mechanisms do not automatically produce a working integrated system. Every interface between stages is a new failure point. The membrane cascade concentrates deuterium, but it also concentrates everything else in seawater. Salt ions foul the membrane surface and degrade selectivity over time. Biological material in coastal water clogs the prefiltration stages. The laser separation cell requires optical clarity in the water stream that raw seawater never provides. And the oxygen-deuterium bond absorption frequency that gives the laser its selectivity shifts slightly with water temperature, meaning a fixed frequency laser loses efficiency across seasons and latitudes. The legacy architecture had none of these problems. The Bruce Heavy water plant drew from controlled freshwater feedstock, operated at stable industrial temperatures, and ran a chemistry-based process indifferent to seasonal variation. It also required 400 acres and permanent grid connection, making ocean-adjacent deployment irrelevant by design. The new architecture discards every one of those constraints and takes on all of the ones the old approach avoided. What made the integrated system work was a processing sequence that treated each constraint as a dedicated engineering stage rather than a compound problem. Seawater intake feeds a pre-filtration module, removing particulates and biological material. A reverse osmosis desalination stage strips ionic content before the membrane cascade, protecting selectivity across long operational runs. The polymer membrane cascade runs at low energy on the clarified, desalted feed stream, concentrating deuterium from the natural baseline toward the target enrichment level. The concentrated stream enters the laser photodissociation cell, where the HDO population is now dense enough that photon flux covers the full molecule flux without saturation. Deuterium oxide collects at the output stage, is compressed, and transfers to storage. The part that almost never appears in public coverage of this program is the AI process control layer. Because the OD bond absorption frequency shifts with water temperature, A fixed-frequency laser drifts out of peak efficiency across every seasonal and geographic variation. The system's control architecture continuously monitors feed water temperature and adjusts laser frequency in real time, like a GPS that recalculates for live traffic rather than following a route set at the start of the journey. The ocean changes. The system adapts. A single modular unit at the pilot facility produced verified output in the range of several grams of deuterium per day. A 20-unit coastal installation running continuously would approach the annual deuterium requirement of a research-scale fusion reactor. No mining, no transport chain, no chemical feedstock. For the first time, the fuel supply for a fusion reactor could be co-located with the reactor itself. Here is the honest picture. The system as demonstrated is not yet at commercial fusion fuel scale. The current pilot output covers a fraction of what an ITER-class reactor requires annually. ITER's design specification calls for approximately 112 kilograms of deuterium per year at full operation. A single modular unit at demonstrated output rates would need to run for years to approach that figure. The membrane degradation rate under continuous real seawater exposure beyond the pilot run duration has not been fully characterized. Fouling behavior in open coastal environments introduces variables that controlled pilot conditions do not replicate, and the laser system requires periodic recalibration that adds a maintenance overhead not present in the passive chemistry of a Girdler sulfide plant. These are real constraints. The program's published assessments do not hide them. What the program did produce was this: the China National Nuclear Corporation Verification Team, working alongside an independent review group at the Chinese Academy of Sciences, certified the integrated system's energy consumption per gram of deuterium, separated at a figure below the Girdler sulfide process benchmark, sustained across the full documented pilot run. That certification is the number that required a second independent review before publication, not because anyone doubted the methodology, because the implication was significant enough that the authors wanted the verification on record before the result entered the literature, and this is the number nobody talks about. The pretreatment stage that protects the membrane cascade from seawater ionic content, the reverse osmosis desalination module, produces demineralized water as a continuous byproduct. At pilot unit output rates, that byproduct stream runs to thousands of liters per day. In coastal communities where fresh water access is constrained, a deuterium extraction installation is simultaneously a water production facility. The fuel extraction system and the water infrastructure share the same capital investment. Now translate the certified deuterium output into ocean volume. The seawater volume required to produce 1 year's fuel supply for an ITER-class reactor using this system represents a fraction of the daily water intake of a mid-sized coastal desalination plant. The ocean does not notice. The reactor runs. The ocean just became a fuel tank for nuclear fusion. If that number surprised you, the next part is going to change how you think about the entire global energy equation. Hit subscribe so you're there when we cover it. The extraction works. The number is certified. The question that followed, the one the global energy sector has been sitting with since the results cleared independent review, is what this actually changes for every program, every institution, and every nation that has been waiting for fusion to become real. For 70 years, fusion energy has been described as 30 years away. The joke is older than most of the engineers currently working on the problem. But underneath the joke is a real engineering history, and one of the threads running through that history is a fuel supply assumption that almost nobody examined closely. The International Atomic Energy Agency's fusion fuel cycle reviews through most of the 20th century treated deuterium supply as a solved problem in principle and an industrial-scale challenge in practice, meaning it was available if you were willing to build a CONDU-style extraction infrastructure and effectively unavailable if you were not. Here's what most people get wrong about that assumption. It was not a geopolitical constraint. It was a chemistry constraint dressed up as an infrastructure problem. The deuterium was always in the ocean. The Girdler sulfide process was always the bottleneck. Every fusion program that designed around CONDU-scale deuterium supply was designing around the bottleneck rather than removing it. What this breakthrough changes is the design assumption itself. Modular coastal extraction decouples fusion fuel supply from industrial-scale chemistry infrastructure. The EU's DEMO program, the UK's STEP reactor, South Korea's K-STAR follow-on program, and Commonwealth Fusion Systems' SPARK project all carry deuterium supply assumptions in their fuel cycle economics. Those assumptions were built on a world where the Girdler sulfide process was the only viable extraction method. That world just changed. What adoption actually requires, and why it is not simple, is worth stating plainly. The membrane degradation problem in open marine environments is a civil engineering challenge that the pilot program did not fully resolve. The International Desalination Association's documented experience with membrane fouling in coastal industrial environments makes clear that biofouling management at continuous operational scale is not a minor maintenance question. The laser recalibration overhead at sustained industrial throughput is uncharacterized beyond the pilot run. Integrating a modular extraction unit into a real coastal facility involves foundation engineering, storm exposure, and regulatory frameworks that laboratory validation does not address. The historical parallel is precise. In 1977, the U.S. Energy Research and Development Administration classified photovoltaic technology as a marginal supplementary energy source. By 2024, the International Energy Agency reported solar photovoltaics as the cheapest source of electricity generation in human history. The limit on photovoltaics was never the physics. It was manufacturing scale and cost reduction over time. The engineers who called it marginal were not wrong about the technology in 1977. They were wrong about what the technology would become. The limit on seawater deuterium extraction was never the ocean. It was the extraction method. That limit just moved. Step back from the engineering for a moment and look at what actually changed. For 200 years, humanity has defined energy scarcity by the accessibility of the fuel. Coal required mines. Oil required drilling rigs and pipelines and tanker fleets and geopolitical relationships maintained at enormous cost. Even uranium required extraction, enrichment, and a supply chain complex. Enough that only a handful of nations could manage it independently. Every energy transition in history has been a transition from one scarce fuel to a slightly less scarce one. The assumption running underneath all of it, so fundamental that it rarely got examined, was that the fuel itself was the constraint. Seawater deuterium extraction does not incrementally improve that picture. It changes the frame. The fuel for fusion has always been in the ocean, in effectively unlimited quantity, uniformly distributed across 70% of the planet's surface. The constraint was never where the fuel was. It was whether we had an extraction method that made the fuel cycle viable. That question just got a different answer. If you made it this far, you now understand more about seawater deuterium extraction than most people who write about it for a living. What was actually proven here is not that fusion is solved. The plasma confinement problem is real. The engineering path to commercial fusion reactors is long, and nobody serious is claiming otherwise. What was proven is that the fuel supply assumption that made fusion seem permanently out of reach. The assumption that deuterium extraction would always require Condu-scale infrastructure, always carry an energy debt, always be the bottleneck nobody wanted to talk about, was an engineering constraint, not a physical one. And engineering constraints, when approached from the right direction, move. Speaking of materials that are changing what we thought was physically possible, if this kind of engineering breakthrough is what you come here for, you're going to want to watch this next. China just invented glass that generates electricity, and the mechanism behind it is every bit as counterintuitive as what you just heard. That video is right here, and it picks up exactly where this one leaves off. If this changed how you think about the future of energy, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think seawater deuterium extraction gets fusion reactors to commercial scale within 30 years, or is the plasma confinement problem still the wall that stops it? Both sides have a real argument. See you in the next one.